Friends, welcome to lecture number 4 of irrigation and drainage lecture series. So, in this we are going to learn basically the soil water relationships, and we are going to see how the water is held between the soil particles, among soil particles, and what are the forces with which these the water body is held within the soil particles. So, and then we are going to talk about soil water and soil water potential and some examples at the end of the lecture. So, here if you see, so clearly if you see, so this one is the water status between these two soil particles, if you am wrong. So, here you have a soil particle here, okay. So, and there is another soil particle somewhere here, okay, isn't it. So, in between these two soil particles, so we are talking about how the water is going to held between these two soil particles, okay. So, assume that this is center of these two soil particles. So, exactly this is the center of these two soil particles. Okay. So, since generally what happens with the nearest part of the soil particles, the water is held tightly. Okay. The water is held tightly. So, here also the water is held very tightly. Okay. But whereas the center the water is held very loose without with less tension. So, that water is called the water which is flowing through gravity or the gravitational water. So, this can easily pass through the soil particles because the tension with which this particular water held is 0 to 0.3 bars, 0 to 0.3 bars. So, generally, so that is what the gravitational water. Then after that, so at exactly at 0.3 bar, the whatever water which is held with the tension at 0.3 bar, it is called field capacity. So, this is very important as far the irrigation is concerned. So, we will be this is the main criteria, the threshold for giving irrigation water. Okay. So, then after that if you see from 0.3 to 15 bar tension. So, the water at which the water which is held by 15 bar tension is called the wilting point. So, the water is at wilting point, we call water is at wilting point. So, the water which is available for the plant lies between field capacity and wilting point, okay, field capacity and wilting point. This is called plant available water. This is a plant available water. Okay. So, then after that from 15 bar to 31 bar. So, the water soil water will be held by some forces or mostly the capillary forces. So, this is called the permanent wilting point. So, here, so at 31 we call this permanent wilting point, and also we call this hygroscopic water hygroscopic coefficient. Okay. So, then after that the water is really tightly held at the soil particle with the adsorption forces. So, or adhesive forces you can say. So, and up to 10,000 bar. So, this is called the oven dry water. So, if you keep, and I think the previous lectures we talked about the oven dry water, if you keep a moisture sample in a oven. So, at the dry sample contains still some water. So, that is so that is called oven dry water, but it is completely dry condition. Okay. So, this is the plant available water between 15 bar to 0.3 bar, and then there is a capillary water that is 0.3 bar to 31 bar. Okay. So, I mean the overall. So, in this slide what we are going to demonstrate is, so the water which is present between the soil particles, okay, is held by certain forces. So, the first one is the gravitational force. So, with the gravitational force water will pass through the soil particles, which is not available to the plants, and whereas due to the two different materials, is a solid and then water, there is always some adhesive forces, right. So, adhesive forces, okay, they are going to keep the water towards the soil particles. Okay. So, why we are talking about this? Because the plants have to extract this moisture except the gravitational water. So, the other moisture really required for the plant growth. Okay. So, so that is the reason we are interested in the water which is held between the soil particles. And so, what these tensions indicates, this is the tension, the bar. So, the bar assume that the soil is completely saturated. Okay. The soil is completely saturated, that means as I said, the soil has the pores, the pore contains either water or the gases. Okay. So, assume that the whatever the voids which are occupied by completely water. Okay. So, when there is a plant, so since plant requires water, the plant extracts water, and whatever this kind of the tiny reservoirs, okay, the tiny reservoir is going to get empty. So, then it get empty. So, then the negative pressure is going to create. So, that means, so this from saturation soil to unsaturated soils condition, it is going to achieve. So, so this this negative or the tension, so that is called soil moisture tension. Okay. So, let us see the so next. So, here the soil water. So, we are talking about soil water. So, as I explained before, it is a gravitational water, right, and the capillary water and hygroscopic water. These are the three water types we need to consider for the irrigation purpose. So, the gravitational water, as I said, it is between 0 bar to 1/3 bar. Okay. It is between 0 bar to 1/3 bar. If you see the picture here, so the water which is the gravitational water is completely saturated initially, and it is going to drain through the soil pores. So, that means this is not going to available to the plants anymore. So, then the capillary water, if you see the capillary water here. So, water is held in micropores, okay, and then so and this is in between 1/3 bar suction to 31 bar suction. So, this is the total capillary water, whereas the water available to the plant is lying between 1/3 bar to 15 bar. This is a wilting point, and whereas the water not available to the plants, the 15 to 31 bar suction. So, it is called a permanent wilting point, and the plants cannot extract any more water, whereas 1/3 to 15 bar the plants are going to show some kind of wiltiness. Okay. So, then the hygroscopic water. So, the hygroscopic water, if you see this hygroscopic water, so this is going to remain in the soil, which is held tightly to the soil particles. So, the soil water above hygroscopic point is a suction which is greater than 31 bar, and of course, it is not available to the plants, okay, and mostly held in soil colloids and move extremely slow rates in the vapor state. So, extremely slow rates in the vapor state. So, this is not going to available to the plant. So, our main focus or interest is the field capacity water. Okay. I am sorry. Okay. So, then the soil water available to the plant, as I mentioned. So, the field capacity, which is denoted with either F c or theta F c. Okay. So, in literal sense, the field capacity is defined as the water content of thoroughly wet soil at surface by irrigation and rain. Suppose you have a field, right, which has water previously by either rain or irrigation. So, that means the field is completely saturated, and that saturated field is allowed to drain into dried soil. So, the top is the top is saturated, whereas the bottom is still dry. So, that the gravity water, the gravitational water is going to pass from saturation to unsaturated zones. So, then the drain through water, the soil profile due to the gravity becomes negligible as compared to plant root uptake. So, the situation when the gravity water flow is going to be 0 or there is no gravity flow, then the moisture content of that soil is called field capacity. So, in that means, so suppose you have rainfall today, okay, so the soil is completely saturated, and then after that event, so there is no rain, and overnight no rain, then the next morning you have gone to the field and checked, the soil is still wet. Okay, the soil is still wet, it is not saturated completely, but still wet. So, that condition is called the field capacity. So, that means whatever water which is saturated, which is being used in saturation is drained by gravitational force, and the remaining water which is retained within the soil pores or soil matrix is called the water is called field capacity water. Okay. So, this condition may reach within a few hours or few days, okay, depending on the soil texture or soil structure and layering. Okay. So, here you have like for example, sandy soil, right, soil texture, you have lot of sand. So, what happened in few hours, the gravitational water is going to drain out. Okay. So, whereas if the clay soils, it takes long time to drain out the gravitational water. Okay. So, similarly the layering. So, you have number of layers, the first layer, second layer, a third layer, and the top layer is for example, it's impervious kind of like semi pervious layer. So, it takes time to the gravitational water to penetrate from one layer to another layer, and it takes time to reach the field capacity level. So, the upper limit of soil water available to the plant. So, this field capacity is also known as upper limit of soil water available to the plant, and soil water content where gravity drainage becomes negligible. So, so the gravity initially is more, then after that started declining. So, then the moment the gravity water is 0, we call that it reached the field capacity, and soil is not saturated, but still very wet condition. So, if you observe during field capacity time, the soil is not dry. So, it is still wet and not saturated. Okay. And as I mentioned, so the soil moisture stress at field capacity vary between -1/10 bar to -1/3 bar. Okay. So, then so next is the field capacity which is affected by several factors. So, as I mentioned, soil texture, layers, organic matter, and also the depth of wetting. However, it assumes as a constant over a growing period. So, I mean when you do modeling or even field experiments or water balance studies. So, we consider field capacity is constant throughout the growing period, and then we decide irrigation based on that. And then this is, of course, this field capacity is a idealized concept, and because salts do not drain to a given water content and ceases to drain further. Okay. And the concept is invalid in the presence of impermeable layer or water table. Suppose if you have a water table lying down the soil and then also the impervious layer. So, what happens if there is a water on top, it enters into the soil through infiltration process, and since there is a clay layer or any water table, it is not going to move further and the water will not drain further. So, that means the gravity water still there in the surface. So, that causes the drainage problem. Okay. And then the field capacity concept may not be applicable to soils with swelling and shrinkages. So, suppose you have a clay soils. So, the field capacity I mean reaching field capacity takes longer time. So, because the soil swell with the water, right, it is not going to drain water anymore down. And then the permanent wilting point here, if you I mean this generally denoted with theta WP here in our lecture. So, it is defined as the amount of water left in the soil when the plants are unable to extract. Okay. So, when the plants are unable to extract any more water to meet their demand. So, during that time what happen if you observe the plants is going to wilt. So, this kind of symptoms you can observe when you look at the plants. Okay. So, that means it requires water. Now, it is reaching the wilting point level. So, this is also called the lower limit of soil water available to the point. Okay. So, one is upper limit and other one is lower limit. So, upper limit is field capacity and the lower limit is the permanent wilting point. Okay. Still some water in the soil, but not enough to be used to plants. So, here water is held by absorptive forces and hygroscopic water. So, some part of water is available to the plant, the other part is not available. That means, you have like 1/3 to 15 bar, of course, this is negative. So, this is available to the plant, whereas minus 15 to 30 bar, this is not available to the plant. Okay, traditionally defined as water content corresponding to minus 15 bar, this is called wilting point. Okay. So, then so next the available water, which is if you consider the lower limit and upper limit. Okay. So, the water which is lying between lower and upper limits. So, that means field capacity and wilting point. So, that is called the available water, that means available, this water is available to the plant. Okay. So, here if you see the water is held solved between field capacity and wilting point. Okay. So, then this is called available, and there is an equation to calculate available water here. So, d or z. So, this is the root zone depth, and theta f c, this is the moisture content at field capacity, and theta w p, this is the moisture content at wilting point, and divided by 100, because this is in percentage. So, we need to divide by 100. So, and theta f c and theta w p all are in volumetric basis. Suppose if you have that in gravimetric basis. So, in order to convert the volumetric into gravimetric or the gravimetric into volumetric basis, just like this, you have to multiply with the bulk density. So, the same equation, if this is in gravimetry, right, this is in gravimetry. So, in order to convert this into volumetric basis, so the same equation can be written d or z into theta f c minus theta w p still divided by 100, but we multiplied with bulk density. So, where theta is gravimetric basic gram per gram. Okay. So, this is gram of water per gram of soil. Okay. So, then you need this is called bulk density. Okay. Only thing the conversion, right. All right. So, here this graph show us for different soils. So, how and also on y axis water per foot of soil, that is in inches water depth in the soil. So, this is upper limit, we call this is the field capacity, and this is the lower limit, this is the wilting point. So, the water which is in between, so that means the water per foot of soil had in between we call the plant available water. Okay. This is called plant available water. So, then so the next is if you compare this coarse sand and a silty clay loam. So, that means one is coarse texture, the other one is fine textured soils, and see how the water holding capacity varies, right, between these fine texture and coarse texture soils. Okay. So, and assume that in the both cases the dry soil is same, and here in the coarse sand the gravitational water is more because the pore size is larger compared to here the tiny pore size. Okay. So, that is why it is very easy to the gravitational water can pass very easily through the pores. Okay. And then the next one is available water. The available water here, since it is a fine texture soils, right. So, it can retain larger water compared to the coarse texture soils. Okay. So, that is the reason if you see, so this amount is available water, this amount is available water, whereas unavailable water here unavailable water is even the smaller, and unavailable water is larger here, because the tiny pores and the water is held strongly with the soil particles, right. So, if you see the water holding capacity, so this is the magnitude and this is the magnitude. So, that means the fine texture soils will hold larger water compared to the coarse texture soils. Okay. And then so, here another concept called readily available water was okay. So, and this is very important as far the irrigation is concerned, because based on this we are going to decide the when to give irrigation, okay, and then how much to give irrigation. So, this irrigation scheduling we call. So, what happens? So, suppose once the field has the moisture at field capacity, and there is a plant which started extracting water from the reservoir, right, through evapotranspiration. We are going to talk about this more in the following lectures. So, this is crop evapotranspiration. So, due to that the water which is held between the soil particles is going to escape through the plant. Okay. So, then there is a negative pressure or negative soil moisture is going to create. Okay. So, that means the water is the soil water is going to deplete, the soil water is going to deplete. So, when that is going to deplete, so from upper level to the lower level, that is called field capacity to wilting point. So, these two levels, so we are talking about this is available water, okay, and due to this ETC, this water reservoir, this is called a reservoir, let us say. So, the level of reservoir is going to decline. So, okay. So, here, so the water which is available to the plant readily, okay, readily available to the plant for getting the higher crop yield is called readily available water. If you see this picture here, so on x axis this water content in percentage, and y axis is rate of evapotranspiration. Okay. So, as I said, the evapotranspiration increases, So, initially this is starting point, then after that due to loss of water, it reaches the wilting point. Okay. So, then the curve goes down to permanent wilting point here, and no more evapotranspiration here. Okay. So, then here RAW, readily available water, what we are talking. So, here if you see the water is which is down up to here, even if you reduce water, even if you wait to replenish water up to this point, So, that is not exactly, if you see this, if this graph. So, here almost this constant, right, theta f c. So, at this point somewhere, even if you reduce, wait till this moisture content give irrigation, it may not be affecting the crop yield, maybe up to here it may not be affecting crop yield, but beyond that, if you still wait for the crops to extract water and not giving any irrigation, that definitely is going to influence your crop yield. So, this the condition up to which the moisture content up to which the yield reduction is negligible is called the readily available water. So, here, generally the readily available water is estimated with the root zone depth, and theta f c, this is the soil moisture at field capacity, soil moisture at wilting point, okay, divided by 100, readily available water. Okay. So, then so the next is next concept is called the maximum allowable deficiency. Okay. This is called MAD. So, this is the term we use as irrigation engineers for most crops. So, this is 0.65 MAD. MAD is defined as readily available water and divided by available water. Okay. This is the fraction of total available water reservoir, and up to which the plant up to which you can achieve the you can achieve no reduction in crop yield. So, that is RAW and AW. Okay. And this kind of irrigation. So, our aim is to fill the soil moisture to the field capacity. Okay. So, if every time if you maintain the field capacity, right, absolutely, no problem, you can achieve the maximum yield, right, but the thing is you have to irrigate frequently in order to reach the maintain this kind of situation. So, that is why. So, and as you seen before the graph, right, when this is theta and the depletion here. So, at some point up to a certain moisture content, so the yield is going to be same. So, why should we give frequent irrigation? We can wait till this point, right, this moisture content, and then give irrigation. Okay. So, here MAD decides this kind of this point basically. Okay. So, at what? At 65% of depletion in available moisture content. Okay. So, that is MAD. So, this kind of irrigation practice called deficit irrigation, right. So, because you are allowing the plant to be a little bit stressed. Okay. So, what is deficit irrigation? The sacrificing the crop revenues to achieve reduction in water and energy. These are two inputs. Okay. So, water and energy costs that exceed the sacrificed crop revenues. So, what happens? You have some inputs, water and energy costs. So, those costs are higher, right, and if you reduce that, and higher in the sense that is exceeding the crop revenue. So, if you can reduce that and sacrificing little bit crop revenues, that is not going to impact much on farm economy. So, that is called the deficit irrigation. So, then the next thing is So, here soil water potential, if you are talking about soil water potential, the whole thing, the water potential contains these 3 components. So, this is the total water potential, and this is gravitational water potential and metric potential, and this is osmotic potential. Okay. So, this gravitational potential we have seen before, the potential which is experienced by the gravity, I mean water, and then metric potential, mostly the capillary water, and then osmotic potential, this is due to the salts which are present in the I mean the soil water. So, normally what we do here, the metric potential, which is the greatest effect on release of water from the soil to the plant, and our main concern is the metric potential here. Okay. So, then so the next is if you are going to see the gravitational potential, metric potential, and osmotic potential, since we are not in this lecture we are neglecting. So, here the gravitational potential, if you see, so this is the component of total potential, so which is due to position of the point relevant to some reference or specific elevations. Here this is the reference, suppose this is the soil stratum, and let us say the point A and point B. So, these 2 points, this is the reference point, and from the reference point if you go up, so that means this is the positive potential, and go down, this is the negative potential. So, what does it mean? So, that means here is the water reservoir, and one guy wants to fetch water from this to this, that means he has to do some work. Okay, he has to do some work, that means the positive work. So, he has to do some positive work in order to get water from this reference line to here, whereas the guy who is inside below the reference line. So, the water is on top of him, he does not need to work much. So, this is called a negative, okay, a negative potential. So, and since the water is very slow in this case in the porous medium, we are not concerning any kinetic energy here. So, only potential energies. Okay. So, then let us see here an example of gravitational potential. So, for example, here the gravitational potential, let us say A and B are the 2 points, right. A and B are the 2 points located at distance 125 mm above, okay, and 75 mm below the reference line. Also determine a change in okay, what we have to find? We have to find out the gravitational potential of points A and B, okay, and also change in gravitational potential between A and B. So, since this is given, see psi G A is given 125 mm, psi B 75 mm, this is negative, sorry. So, this is positive, right. So, psi G A is positive because this is above the reference line, above the reference line. So, that is why this is positive, and psi G B is negative because this is below the reference line, right. So, then this what is the difference? They also determine the change. The change is G A minus psi B. So, 125 minus of minus 75 total 200 mm is the gravitational potential, change in gravitational potential. Okay. With reference to, at this point the change in gravitational potential from A to B is 200 mm. Okay, then the next is the metric potential. So, the metric potential here, the basically when we are talking about the soil moisture stress, right. So, gravitational potential that goes through gravity. So, whereas the metric potential we are talking, so which is the water is held by soil particles the mostly. So, the application of pressure or suction, okay, to the soil water causes the change in water potential. So, this change in water potential is called pressure potential. So, here for example, the pressure potential could be positive or it could be negative, depends on the increase or decrease in potential energy with respect to free water atmosphere. Okay. Generally in atmosphere if you are talking about the potential or the metric potential atmosphere is a 0. Okay. I mean the water table level is a 0, and when you go up or is going up, that means when the water is depleting from the soil surface and the negative pressure is going to create. Okay. So, for example, here if you see, so this is called a tensiometer, right. This is a tensiometer which is installed in the soil. So, it has a porous cup at the bottom. Okay. So, and the other side, the top, which is connected to the manometer. Okay. So, initially the water I mean the tube is filled with, the tensiometer is filled with water completely before installing it, and then you have the initial water level, okay, in the manometer. Then after that, after a few days, if you see, the manometer level is going to get down, because this water, I mean the water which is present in the soil is going to deplete because of the water taken by the plant. There is a plant takes water. So, then the water which the soil water which is surrounding the porous cup is going to deplete, and since there is a water reservoir available, that is going to come out, from the ceramic cup, and here there is an empty space. So, that means there is a suction is going to create, and this level can be monitored here. This is called metric potential. Okay. Under unsaturation condition, soil water pressure is negative, and the negative pressure potential is also known as capillary pressure or metric pressure potential, or suction, or simply tension. Okay. There are some relative, all these terms are relative. Okay. And then let us go to the next slide. So, here is the metric potential. So, the metric potential has as I said, this is a pressure potential, and water table, for example, here we are talking about the water table, which is the locus of atmospheric pressure in the soil water system. So, this is unconfined aquifer. So, this is a water table. So, exactly at this point, this is atmospheric pressure, because this is open to the atmosphere. So, the same atmosphere, whereas here in the down, this is suppose at the point here, this is the point of interest. Okay. So, this is the point of interest. The total potential, here H, which is two components, right. So, one is pressure potential and the other one is elevation. So, this is the elevation, and here we are, as I said, we are not considering the other potential. So, that is called the osmotic potential, that is we are not considering here, and also kinetic energy, because the water is, water moves very slowly, we are not considering that. So, the hydraulic head, the total hydraulic head, and the pressure head and the elevation head. So, elevation, so here there is a pressure head, and then the distance from here to here, so that is called elevation. So, okay, so here this is a Z, okay, here the pressure point, right. So, and then this is the total head. And then, for example, here in this example, if you see, so there is a 100 mm soil profile, okay, 100 mm sorry 1000 mm soil profile, which is divided into 100 mm sections, okay, 100 mm sections. So, water table, let us say water table at 600 mm, okay, distance from the top. Then the question is estimate pressure, gravitational and hydraulic, the total heads, okay, throughout the profile at an interval of 100 mm, assuming that solute concentration is negligible. That means, osmotic potential is negligible here. So, if you see here the depth is, so this is the depth 100 mm, 200 mm, 300 mm following, and this is the H. So, since this is your reference, so above above the reference you get a negative, okay, above the reference you get a negative, because this is elevation, okay, this is the pressure. So, above, this is the pressure. So, pressure is negative above that, and whereas pressure below that is a positive, and Z, this is elevation. So, above that the elevation is above the water table. So, the elevation is positive, whereas below the water table elevation is negative, and I mean the total hydraulic head is going to be 0 with this negative and positive effects. Okay. So, how to estimate or sorry, how to measure the soil water potential here? The soil water potential is generally measured with tensiometers. Okay. So, the tensiometer has a long the tube, and the bottom there is a ceramic porous ceramic tip, and the top there is a water reservoir, and there is a gauge, vacuum gauge, which is attached to that, which is read between 0 to 100 centibars. Okay. So, this is but if you observe this, so with this tensiometer we can measure only 0 to 0.75 bar, okay, only 0 to 0.75 bar. So, so if you observe the field capacity 0.33 bar, right, 0.3 bar, 1/3 bar. So, you can measure that, and then there is a 10 bar or sorry 15 bar. Okay. So, you can only practically with using tensiometer you can measure 0 to 0.75 bar. So, this picture shows how to install it in the field. Okay. So, how is going to work? Because initially before installing the installing it in the field, so this complete this column, right, is completely filled with water. Okay. So, that means it is complete reservoir. The moment you install in the field, right. So, the water which is surrounding I mean the soil water which is surrounding the cup. Okay. So, if suppose this is initially saturated, then it, after few hours it is going to be equilibrium. So, then due to the soil water depletion, the water is going to escape from tube to here, and here the water level is going to decline, and that creates the vacuum here, and the vacuum will be measured. Okay. So, that way this tensiometer is going to work. And then next there are different kind of tensiometers if you observe here, right. So, this is a simple vacuum gauge kind, and the other one is cable to data logger. You can directly connect it to a data logger, and you can also record the soil moisture tension at different time intervals. So, here there is the other one is the pressure transducer based. So, this is also continuous base. So, here there is a digital readout, you can directly attach to the readout and get the reading. So, here there is a needle. So, the needle the moment water goes down, the suction will be read through suction will be sensed by transducer, pressure transducer, and that is read by digital readout meter. And so, with tensiometer also we can indirectly measure the soil moisture. So, for that what we require is the soil moisture release curve. So, how do we extract, how do you get that soil moisture release curve here? Yeah, that is one thing. The before that I would like to mention there is another is called sorry. So, there is another the equipment that is electrical resistance blocks, the gypsum blocks we call. So, we can also use gypsum blocks to measure tensiometer, measure the soil moisture tension. So, it measures the soil water potential in tension, and then so what basically it has. So, it has the electrodes inside, and this is gypsum block. The electrodes are connected to resistance meter, Okay. So, then the water then the when there is a water the electrical conductivity will be more, when there is a less water electrical conductivity will be less. So, based on that principle this gypsum block is going to work. And here in order to make the water content and the soil moisture tension. So, there is an apparatus called pressure plate apparatus. Here the series of pictures show the operation. The first thing is this is called a pressure plate. So, which is connected to a vacuum pump. Okay. So, the vacuum pump will allow take out the the pressure or create suction inside the chamber basically. So, it contains the porous plate here, if you observe this is the porous plate, and then the samples are kept on top of this. So, like this is a porous plate and the samples, these are all completely saturated samples. Then you put the lid on top and then tightly screwed. So, because there is no leakage, and then you are going to set the pressure here. Okay. So, then you run the instrument, that means you keep the vacuum for overnight or 1 or 2 days. So, then after that remove the lid and take out the sample and weigh the soil moisture, I mean measure the soil moisture using what do you call oven method. Okay. So, then that corresponding to the corresponding I mean the soil moisture corresponding to the soil corresponding to the vacuum you created here. Okay. So, that way you can measure the soil moisture at a particular soil moisture tension or soil moisture tension. Okay. So, here once you do that, you are going to get this kind of graph. So, the soil water release curve we call the curve matrix curve of metric potential or tension versus water content. So, here this is available water and soil moisture tension, that is in bars. So, for different like sand, loam, clay. So, this curve is initially for the less negative pressures, the soil moisture is higher, then after that it is going to decline. And here in order to take out the moisture content, lower moisture content, you need to invest higher pressures. Okay. So, that is the reason here. So, if you see this, the curve for a particular moisture tension, So, sandy soils. So, for 5 bars sandy soils can only retain 20% moisture, right, whereas clay soils can retain 50% or 45% moisture content. That means, the retention capacity of clay soils is higher than the sandy soils. Okay. So, then this shows how the soil texture is going to influence the height of capillary rise. So, that means, you have a fine textured soils, fine texture versus coarse textured soils. Okay, coarse textured soils. So, this is an example of coarse texture and this is example of fine textured soils. So, since fine textured soils will have smaller pores. So, the capillary rise is going to be higher compared to the capillary rise in case of coarse textured soils, this one. So, that means, the pore size is very important in also that influence the metric potential. Okay, thank you for your patience.